my regular voice. Okay. And about the updated versions of the slides. So they're on my lab. www.li.fr. Tilde, my name without the N. UB, capital letters, and then this. So it's continuously updated. So if you want to see them back, maybe wait for a few weeks. And there's also a set of lecture notes for the moment by Gabolu Koshi, who already used them in the machine learning winter or summer school that took place in Canberra in February. So you can download that from Gabor's webpage. So I think the web address is this one. So University of Pompeu Fabra and Tilde. Use Google to check that everything is in order. So well, I'm not presenting exactly the material Gabor covers, but there's a very non-empty intersection. Okay. So thanks for coming back. And we'll try to go on this subject to go right down on concentration inequality. So we're supposed to be roughly around here, and we'll see that we are right here. So this is a long blah blah concerning the present situations. So let me recall a few facts from yesterday's talk. Well, the starting point was those have been Bernstein exponential inequalities for sums of random variables. And some independent random variables. So there is a feeling, and it's actually true, that in learning theory and in many other subjects, we need results that have the flavor of those exponential inequalities. That is, they are non-asymptotic, they deal with the full tail behavior, both moderate and large deviations. And they deal with functions that we are not able, or do not feel able to represent as sums of independent random variables. And I tried to give you a flavor of the kind of quantity I'd like to deal. For example, this random interval packing problem, which is not some independent random variable. Then I skip something which is important, and I will again make an allusion about it. You have to keep in mind that there are very different paths to get to concentration inequality. There are these, say, 5 methods. And historically, martingale methods have been very important because this is a very important subject in probability theory at large, and because it's not always feasible to encode a function of interest as a sum of independent random variables. But thanks to a device that is explained in slides, if you want to download them, there is some kind of universal device named the Doog embedding that allow you to represent those weird functions of many independent random variables as a sum of martingale increments. And there is a lot of technology to deal with that. So in principle, we could do everything with martingales. Actually, all the conceptual material concerning what is nowadays used for developing concentration inequalities with martingales was available in the mid-70s. problem is that it turns out to be sometimes not user-friendly. I mean, the quantities that show up in the martingale approach remain, you know that they are the right quantities, but they are difficult to deal with. And so there has been many, many incentives to develop alternative methods. And this has been one of the grand achievements of Michel Pellegrin, using intuitions from geometry and functional analysis. And what I want to present here is something that a posteriori we trace back to the Differential inequality I introduced yesterday. So it didn't happen in that order. And which is that the big idea is that we want to play Markov inequality in different contexts. The cheap context is playing Markov inequality with the square function. So this is the French football league. And if you want to have sharp-tail inequalities, you need to play Markov inequality with the exponential function. This is Champions League. And today, we want to put Efrenstein inequality, the Efrenstein estimates, into the Champions League to boost them, to upgrade them. And this, I will try to do that with the entropy method, the so-called entropy method. And we see that in some circumstances, which show up sometimes in learning theory, the Efrenstein estimates turn to be really transparent. Okay? So yesterday I forgot to tell you that you are allowed to ask questions. There is no final exam. I will try to give as much information as possible, so no tight schedule. Feel free to interrupt me. But please don't ask too difficult questions. So we want to play Markov inequality with the exponential function. So it means that we need to control that guy, or rather this one, the log Laplace transform of z, which is any function of interest. But we'll first go back to Gaussian setting. Gaussians, they may be an illusion, an asymptotic mirage, but I mean, they provide us with nice benchmarks. You know, things turn to be simple in the Gaussian world, and we know that if we can mimic in the finite world where we're living the Gaussian behavior, we're not far from the best we can find. So, actually, we will try to achieve the control of our log Laplace transform using a kind of bizarre functional inequalities that are called logarithmic Sobolev inequalities. So, in order to introduce those inequalities, I need to get another concept. I will overload a name called entropy. So, I take any positive function, and I define the entropy of f, and there implicitly I'm talking about, with respect to a probability distribution, as the expectation of f log f minus expectation of f times log of the expectation of f. So, this is expectation of a certain function of f minus a certain function of the expectation of f. Oh. So, if you have been exposed to information theory or to statistics using the fieldback information, you have seen quantities that are really related, but somewhat different from this one. So for a moment, forget your background knowledge and consider that entropy, this is that. forget about channel. Well, so Jensen inequality, which already showed up yesterday, tells us that as x of x is a very convex function, this is always positive. So our goal now will be to upper bound the entropy of F using something more intelligible with respect to F and with respect to the underlying distribution. And we want to develop some kind of anti-Jensen inequalities. And so entropy is like a variant, something which is convex, and we can do that as an exercise. And now I will introduce you to the mother of all log-Sobolev inequalities. The Gaussian logarithmic Sobolev inequalities. Inequality introduced by Leonard Gross in 1975. It tells you that if the underlying distribution is a Gaussian, the Gaussian may be a 100-dimensional Gaussian or an infinite-dimensional Gaussian. Then, if f is a regular fraction, a smooth function, the entropy of the square of f is upper bounded by 2, is time constant, times the expectation of the squared norm of the gradient of f. So this is a relation between entropy and inertia. So, and you may notice that this was developed in the early 70s for the purpose of quantum field theory. So this is the second connection between quantum mechanics and learning theory that we need today. And I hope you enjoy this from history. So what? What is the relationship between this and that? Well, actually, we can play this log-Sobolev inequality with functions which are exponential of lambda f divided by 2. So if you take the square, it's equal to the entropy of exponential of lambda f. You use the chain rule from high school and execute that. Lambda squared divided by 2 exponential square gradient of f times this guy. And with that, we can do something really nice that will allow us to upper bound the log Laplace transform of f, which is z. And this is done by a trick that is called Herbst argument. So, the idea, and this is an idea that shows up in all the variants of the that relate log-Sobolev inequalities with concentration of measures theorem, is to derive a differential inequality satisfied by the log Laplace transform from the Gaussian, also from the logarithmic Sobolev inequality. So here, we assume that f has a bounded gradient. Say, think about the Lipschitz, uniform Lipschitz function. And for the sake of brevity, use this notation. So if you have done some physics, it's like a free energy, I think. So, and you have made that kind of relationship. So you have that. And then the Gaussian logarithmic Sobolev inequality turns out to be translated into this differential inequality, which is really integrable. Even I can do that. And then rewriting, which is a powerful computer science technique, allows you to get that. And you're done. You're happy. This is exactly what you would expect for a Gaussian random variable with unique variance, oh, it's wonderful. Actually, if you play the Markov game, you end up with that. It means that any uniform Lipschitz function for Gaussian enjoy Gaussian terms. And that the pseudo-variance term is this uniform bound on the square of the graph. Yeah, if I would, for the sake of historical completeness, I should say that the first proof of this is due to Chirelson. Actually, Ibrahimov, Shudakov, and Chirelson in 75, and it used a technique which is much more Martingale flavored than this kind of technique. Actually, you have to understand that logarithmic Sobolev inequalities are part of the concentration business, but they're also part of many other areas of mathematics. So I think the connection between logarithmic Sobolev inequalities and concentration of measure theory was discovered somewhat later. But anyways. So this is a message. Actually, we can replay this Herbst argument a little bit. And this will allow us to introduce a very useful trick that is very important when dealing with product measures and dealing with real-life applications. Well, pseudo-real-life applications. So now we will forget about the assumption that the gradient is uniformly bound. We just assume that it enjoys some integrability property. And we will call this inequality a decoupling inequality. It allows you to separate these expectations where you meet two persons that you don't want to be together, Z and W, and you can upper bound that by the entropy of exponential lambda Z times this product. And this is a, yes? Yeah, solution. It's a directional characterization of entropy. Which, well, I will come back on it a little bit later.
So for any W.
Yeah, well, provided all those expressions have a meaning. But I assume that everything that needs to be measurable, to be finite, is measurable and is finite. Okay? This is the consequence. This is the consequence of that. It's just very random. So, if you go back to this inequality, we were in a situation of that kind. So here we have our W, and here we have exponential lambda Z. So we use the decoupling device, and we end up with this inequality. So after little rearrangement, we get that. And I won't bother you with the details, but this, you end up again with a differential inequality of that form that you can approximately solve. And the final result, which is the thing to be remembered, is at first sight, is this one. Now, the log Laplace transform of f or z is upper bounded by something which is the log Laplace transform of the squared gradient of f. So, provided this quantity is finite, we've got a handle on this one. Under in a setting which is significantly more general than the uniform boundedness setting. For example, this gives you a handle on the square of a Gaussian random variable, on a sum of squares of Gaussian random variables, that is type 2 random variables. Yes? Theta is a dummy parameter, something that you can play with. And for example, I developed this inequality, and then I realized that there is a uniform bound on that. Then I can take theta towards 0, and I get back the old Gaussian concentration inequality, the first one. So theta allows you to trade the behavior of the squared gradient. This is some tuning device, like the one we saw in SVM technology. So now, questions? Other questions? We're trying to play that not with Gaussian distributions, but with Quebec distributions. Why? So why? Because actually, this nice Gaussian logarithmic Sobolev inequality is kind of a trademark of the Gaussian distribution. Things are not so nice for others. So what we need is first modified logarithmic Sobolev inequality. We need to have something different from the square gradient on the right-hand side. First, because in the space we're talking about, those product spaces, there may or may not be any natural notional gradient. So we need to find something else. And then we need to develop analogs of the Herbst arguments. So we get modified logarithmic Sobolev inequalities, and we will have to use modified Herbst arguments in order to get what we want. That is a nice control on the log Laplace transform of our variable. So the general form will be that, and actually we will focus on functions that are exponential of times a certain function, then they're something which that we think about as an energy, but where the physical intuition may be somewhat vague. So actually the grandmother of logarithmic Sobolev inequalities is the Sobolev inequality for balanced Bernoulli random variables. So those sophisticated variables that take values +1 and -1 with probability 1/2. So don't forget that in all this concentration business, even if it's somewhat pedantic from time to time, the essential setting, this initial setting, is a two-point space. And everything is then taking limits. There, instead of the gradient, you have some kind of discrete gradient, how the function differs from between 1 and -1. So now, if we want to develop the nuts and bolts, there is actually a two-step strategy. The first step will mimic what we already met for the Einstein inequality. This is a tensorization. And at the beginning, we have the entropy of the function of many random variables. We will upper bound it by a sum over all the random variables. So this quantity of expectation with respect to all random variables except one, xi, of what? Of the entropy of z with respect to the remaining random variable xi, given that all others are fixed. So it's like reducing in some way a multi-dimensional integral into a sum of one-dimensional integral, which are much easier to deal with. But for the Einstein inequality, when this had been done, we were over. It was finished. We were happy. There's a price to pay for the loss of other inequalities. So we still have to work and to upper bound the entropy with respect to the single random variable. And this will rely on the not so well-known property of the logarithmic functions, which is that log of x is smaller than x minus 1. So, tensorization. Let's go back. I will skip many details, but on the reasoning that led us to the Herbst inequality. Again, this will depend on the convexity property and on the fact that the entropy, just like the variance, is a functional that maps a certain set of random variables live in a cone of a vector space onto the reals. And it turns out that this function is a nice convex functional. Being a nice convex functional, it can be represented using a duality formula. That is, as a supremum of linear or affine functions. And so here is the representation. Don't remember who found that one first. Many people have been credited for it. And from that we can deduce that the conditional entropy with respect to x2 is larger than the entropy of the conditional expectation of z with respect to the remaining variables, here x1. Actually, the proof is, I think that the important thing is not n random variables, it's 2. Because we can always group the first n minus 1 into one random variable and consider the last one as a second. And we make no assumption about identity. They are independent, but they may be really different. I let you read a little bit so that I can rest. So here we use this duality representation, and T is somebody that depends both on x1 and x2. We play the telescoping sum game by introducing here the expectation of T with respect to x2. We average on the second random variable. So it's the expectation with respect, the conditional expectation with respect to x1. Then it doesn't hurt to maximize for this guy and for this guy separately. It can just increase our guy. But then, looking at that, we recognize that we can put the expectation with respect to x1 outside, and then we end up with this. And here, this turns out to be the expected something that turns to be upper bounded by the entropy, the conditional entropy with respect to x2. So this is the proof of the tensorization of entropy. Now, we play the dirty game with the logarithmic functions. We will deal with each of our summerhands separately. And say that actually from this we can easily follow that for any fixed u, that this upper bound. And this means that we can upper bound the entropy of F by that. So we would need equality if we were taking the expectation of F. If we can take something else, something which is fixed. So think now that we have tensorized our entropy. So we have in each sum n some kind of context that depends on all random variables except xi. and we consider the entropy with respect to xi. So our u can be chosen as any quantity that depends on everybody except xi. So this is why I call it gi. So this is a quantity, a function of those ones. Those two. This thing is there. And combining with the tensorization property, we end up with this. And I should have put gi with every sample. And then we are really well equipped. With that understanding, we can actually derive almost all the logarithmic Sobolev inequalities that are known in nature. So if we specialize to functions of a certain form, well, things turn quite pleasant, because we decide to take f an exponential of lambda z and gi as exponential of lambda zi. Then we can play some rewriting and end up with, who's that guy? This is tau star, the guy which showed up in the derivation of the Bernstein inequality. This is exponential of x minus 1, the log Laplace transform of the Poisson distribution. So this is the first distinguished modified logarithmic Sobolev inequality. And in this form, this is the way Pascal Massard derived it in 1998. So how can we use this? So we are equipped with that. So let's think about it. Assume that z is larger than vi. This is the context we met with the random packing problem. And think that lambda is larger than 0. Then for x smaller than for negative x, this quantity is bounded by that. So we can use this upper bound to get this inequality. So then we can call that v. And we get that. So this is very much the same expression that we had in the Gaussian setting. But instead of the square norm of the gradient, now we get v. So we can play the same differential game and end up with that. Yes?
Why is lambda zi minus z smaller equal than 0?
Sorry, I don't understand.
So this only for x smaller equal than 0, so why should that be true for lambda zi minus z?
I assume that z is larger than zi. Assume that lambda is larger than 0.
Oh, okay.
So we're in a good shape. So the message here is that we have achieved partly our goal. That is, we have a relation between this log Laplace transform and the log Laplace transform of something that we already met in the Einstein estimate. We have put a condition here. We pay a little price, but we already did something. We have boosted the Einstein estimate. It's now allowed to play in Champions League. Well, let's go further with that. So, and we will tackle, actually, derive the concentration inequality for the random packing problem quite easily now. Well, semi-easy. Actually, we assume now that not only we have z larger than vi, but z smaller than vi plus 1. And then we should notice notice that complexity strikes back again. Tau star is a very complex function. So we can say that z minus zi is something between 0 and 1, and that this quantity, this is a convex combination of minus lambda and 0. And we use convexity and get that. So, taking back our modified log-Sobolev inequality, we get this expression. If, just as if in the context of the random packing problem, we have also this upper bound, we end up with this. We still don't know whether this is useful, but you have to admit that this is nice. So the entropy of exponential lambda z is upper bounded by tau star minus lambda times the expectation of z exponential lambda z. Well, if you're courageous enough, you can say it and solve the differential inequality. So this is another modification of the Herbst argument. It requires a little bit of ingenuity, but it will lead you to this inequality. So, and this has really a strong meaning. So the log Laplace transform of a function, a random variable that satisfies this condition and this one, which has been called self-bounded function by Emmanuel Riot, behaves actually exactly as the log Laplace transform of a Poisson random variable with expectation of C. So what we characterize here is that self-bounded functionals do enjoy a Poissonian behavior. So we capture something which is somewhat different from the Gaussian behavior. And we will meet tomorrow several people that fit into this category. And if we optimize over lambda, it will tell us that the tail behavior is this one. So we have a Bernstein inequality for those people, and our estimate of variance is expectation of z, which for those functions is exactly the Bernstein estimate of the variance. But, I mean, there is not a single modified log-Sobolev inequality. If you go through the literature and look at the work of Emmanuel Riot and then of Olivier, you will see that, I mean, this is not the end of the story. You can get something better in certain circumstances. It's harder, so I won't talk about it. But another very important and fruitful development is to look at the other way we carried out the Bernstein. So there was this possibility of comparing z with a certain zi, which does not depend on xi, and which is deterministic when all other variables are known. But there was also this possibility to look at a random perturbation of z, which I call z exponent I, where we replace the I variables by taking an identical copy for x prime I. And, well, I skip the details, but then we end up with a symmetrized version of the modified logarithmic Sobolev inequality. So, this animal, where on the right-hand side you still have exponential of lambda z, a certain function of the increment, and where you can allow yourself to just consider the positive increments, c minus ci positive, and where psi is defined in that way. So x times exponential x minus 1. So this is a function that roughly Laplace function, and which looks like an exponential in the positive part, which looks like something linear when x is negated, and which looks like x squared when x is around 0. But anyway, we can just notice this and use the fact that we consider positive increments to derive this. So, which is a connection between the entropy and lambda squared exponential expectation of e to the lambda z times v plus, our second Ehrenstein estimate. And this proves to be also very useful planning, because we can again play the decoupling device that was useful for the Gaussian and for the diffuse modified logarithmic inequality. And we end up with this some kind of exponential Ehrenstein inequality. So theta is again a dummy variable, a parameter that can be used to get to vicissitudes of life. And we again end up with a relation to bound between our log Laplace transform and the log Laplace transform of v plus. So yet again we have boosted the Ehrenstein estimates and allowed them to play the grid game. So this leaves us with some kind of now a modus operandi. You may ask, but this guy is really crazy. He talks about things. What is the relationship between that and the theorem? I hope there is one. So, but the modus operandi is that, well, if you don't apply the tensorization property or the transformation argument afterwards, I think at first you can forget about that. You can tell this is vaccination and immunize. But you can use those kind of stuff as black boxes. So you end up with a certain function that you believe should be concentrated. Simulations perform so nicely that you should be able to say something meaningful about it. So then you can play with the v or v plus, check whether it's nice. Then you may end up with v or v plus, which is upper bounded by an affine function of z, and then you can pick up results in the literature that will give you some kind of Bernstein-like inequality. Or you can even end up with v plus or v, which is a constant, and then everything is okay. You have a Gaussian behavior. Or you may just end up with v or v plus, which is simpler than z, and say, well, we play again the Max-Sobolev game, and look at the increments of the v of v or the v of v plus to get a handle on that. So things that will look more a bit, or that have to be done in the future years, are quantities that have shown up in Bernard's course. For example, the difference between the supremum of the full risk in your family and the empirical risk for a given sample. Does this concentrate for reasonable functions around its mean or not? Well, the empirical DC dimension of certain distinguished functions lasts, or the Batch-Hedron dimension, the empirical DC entropy, and many of those quantities that try to capture capacity of a function class. I mean, it's very meaningful to try to check whether they are concentrated or not, because this can enter into model selection strategies. Things, I don't know, maybe number of support vectors in certain settings could or could not be concentrated. Well, I'd like to show you modified log-Sobolev inequalities in action. Actually, to show you that there is something to win from that by dealing with something which has provided concentration inequalities with some kind of patent of mobility. I mean, this is a theorem by Michel Talleyrand from the mid-90s that has received very much attention in the business of random combinatorics. I mean, there's this book by Michael Steer about the relationship between probability and combinatorial optimization, and the last chapter is devoted to the complex distance inequality. So let me talk to you about, introduce you to this notion of distance. Well, we consider a product space and a set A in this product space. Then you will play variations on the Hamming distance in this space. Have everybody met already the Hamming distance? Who has met? So this is a distance that you can define in any product space. Very useful in error correcting code analysis. And so the Hamming distance between two vectors is just the number of coordinates in which they differ. And we normalize this by 1 over square root of n to forget the distance, the dimension dependence. So d alpha, where alpha is something which is a unit vector in the n-dimensional Euclidean space, can be regarded as some penalized Hamming distance. Yes? You don't like this square root of n? Because sum of 1 over square root of n to the square, n times this is equal to 1. This is the main reason, as far as I understand. So, and you may play with that. Huh? The Hamming distance is obtained by taking all the alpha I equal to 1 over square root of n. And Talleyrand's distance is saying that it's just the maximum or the supremum over all the choice of alpha with norm less than 1, Euclidean norm less than 1, of those penalized Hamming distances. So this is a way to say that if somebody doesn't belong to the set A, we try to define him as much as possible. He has to pay a price, which is this distance. And Talleyrand inequality, which proved to be very influential, is just asserting that if you have a set which has a large probability, a set with probability around roughly 1/2, and these are the important sets in product space, then nobody is really far from that set with respect to the Talleyrand distance. Probability that you are greater than t is exponentially declining with t. And with that, and with a lot of ingenuity, it's a little bit more than ingenuity, it's actually wizardry, he was able really sharp deviation inequalities and search for configuration functions like the longest increasing subsequence in a random permutation, or the random Euclidean traveling salesman, or random bin packing. These are really problems that keep people in theoretical computer science busy. Minimum spanning trees and outputs. It's kind of Swiss Army knife. And so why should it be concentrated? There actually, Palermo, Macron, Dembo, and others have all different proofs. And we have a proof using the entropy method, actually our exponential Einstein inequality. That's, in our opinion, quite transparent, moderately transparent. It relies on the fact that actually the diagram distance can be represented as a saddle point. So if you denote by calligraphic M of A set of probability over the set A, you can describe the distance from a certain vector to A as a soup of an int of a certain quantity, which is linear with respect to the choice of the alpha, and which is also linear with respect to the probability that you assign on the set A. Mu here has nothing to do with mu for vector machine. It's just the probability on A. Okay. This actually comes from a generalization of von Neumann min-max theorem, which is due to Motion, and which may be a very convenient tool. I'll review that. And actually, equipped with this opinion, this representation of the Talagram distance. So, thinking of the Talagram distance as a saddle point, well, you can find out that after some few lines of reasoning, B plus B here is upper bounded by 1. So it may be variance of the diagram distance is no more than 1, because the expectation of P plus is just an upper bound of the variance. If you look at a worst case approach to this quantity, you would get something like square root of n, or n, for the variance set of n. So, playing the game, place it there. Playing the Einstein inequality, you do that. And playing the exponential Einstein inequality by taking theta to the infinity, is you there. Then you have to, that can outline some way the feature of the concentration of measure approach. Here I've been talking about deviation of Z around its mean, around its expectation. And I said nothing about this expectation. And this is really one of the trademarks of the concentration of measure approach. You separate the analysis of deviations from the analysis of mean behavior. This is different business that can be handled in different research departments. And you can do that several papers, one for the expectations, one for the deviations. Well, it's socially very beneficial. And but the probability of being in A is the probability that your Talagram distance is 0. So it's also the probability of that the Talagram distance deviates from its mean by exactly its mean, its expectation. So, equipped with that, you can end up with this relationship, which nicely translates into this. And then you end up with that. And using, say, this exponential Differential inequality plus the min-max theorem, you end up with a version of Talleyrand's distance, Talleyrand convex distance inequality, which is, the concepts are not as good as his, but that you can tell back to your grandmother. Because, I mean, in Talleyrand's proof and all the others, there are some things from some tricky analysis things. If you have not worked on Polyas-Seger for years, you don't know that. You can forget. Well, I think it's time to stop.